Hey there. So in this series of lectures, we'll begin talking about the Pleistocene glaciations, and then next Tuesday we'll resume that conversation and really talk about mechanisms for the Pleistocene glaciations. Today the focus is really going to be on how we know what these historic temperatures are, what historic atmospheres were even. There are a few key terms that we'll be talking about in this lecture. Again, I'm providing these for you mostly as a study guide. There aren't many for what we'll be talking about today. The most important things that we'll be talking about today are primarily conceptual. So how do we know what historic oxygen concentrations were, how do we know what previous carbon dioxide concentrations were, and then how do we know what previous tar? And so just to put things in perspective, here's another look at geologic time. Note that unlike the diagram that we looked at in the last lecture, the y-axis is not to scale here. Everything that we talked about in the last lecture is Precambrian. And then a lot of what you did in your in-class activity is really focusing on after life emerges in the Phanerozoic. And so we could talk about divisions of geologic time in the coarsest sense, when we're talking about the Precambrian versus the Phanerozoic eons. As we go finer and finer in time, we get into epochs, eras, periods, epochs, and then ages. And where we'll end up today is with a discussion of the Pleistocene glaciations, which is in the Quaternary period, in the Cenozoic era, in the Phanerozoic eon. And it's actually fairly modern. We live in the Holocene, so the Pleistocene was the epoch that was just before the Holocene. If we do put the y-axis in a proper scale, what we're talking about is way up here. It's a really small division of time. And really this is where we ended up at the end of the last lecture. This is also another diagram that you saw in the last lecture. So this feature that you see here was snowball Earth. And when snowball Earth essentially melted and oxygen and ozone were present in the atmosphere, that was when life could really emerge with the Cambrian explosion. So this is an important diagram because it shows what the global temperatures were historically relative to the mean, which is shown by this line. And so as soon as temperatures approached the average over geologic time, that was really when life could emerge. But this really creates a big question, which is how do we know what mean global temperatures were, and how do we know what mean global precipitation was? One of the things you'll notice about global temperature is that during the Quaternary, it fluctuates quite a bit relative to long-term geologic history. And a lot of these are the Pleistocene glaciation about today. But let's talk about how we know what we know. We know what we know from what scientists like to refer to as proxy climate records. So they're called proxies because we can't go back and measure historic carbon dioxide concentrations within the atmosphere, with a few different exceptions. But we need to infer what climate from things that are strongly responsive to climate. So the one exception is that we can take ice cores from Antarctica, which go fairly far back into geologic time. And we can actually probe these bubbles within the ice cores and figure out carbon dioxide concentrations in the atmosphere during that period of time. But then we have to link that up to a date. So how do we date these ice cores? Well, bubbles are not the only things that you find in ice cores. You also find insects, minerals, ash preserved within the ice cores. And so where there are minerals, we could use radiometric dating. Where there are insects and ash, we can do carbon-14 dating. But one thing is that this is pretty limited in terms of how far back we could go in geologic time. So from carbon that's also present in the ice, we're really limited to about 45,000 years before present. I'll just use the YBP acronym for years before present. And if we use other isotopes in ice, we could really only get back to around 400,000 years before present. So the verdict is that in terms of being able to determine historic CO2 concentrations, this only gets us to the medium term. It wouldn't, for instance, be what we would use to infer that during the Archean era, the concentration of greenhouse gases was really high because CO2 was really high. In order to make that inference, we have to use other options. So really we only get back to 400,000 years before the present with this approach. And what you can see is that even during that period of time, carbon dioxide fluctuated quite a bit. So this last little segment here is the Keeling curve. Remember, that's what I presented on the first day of class. That's the standard hockey the hockey stick increase in carbon dioxide over time, but it's barely a blip in the span of the past 400,000 years. So if we want to look back further in time, we have to use isotopes. And the isotopes that we use to make inferences about historic CO2 concentrations are carbon-13 isotopes. Now, these are found in carbonate rocks. Okay, so the source here is carbonate rocks. So naturally, as a global average, carbon-12 makes up most of the carbon pool, 98.9% of the carbon pool, whereas carbon-13 makes up about 1%, and carbon-14 makes up a really, really trace amount. When we're doing this dating on carbonate rocks, we're really looking at the carbon-13 concentrations. And the way this works is that there are certain processes that lead to what's known as fractionation of isotopic ratios. So fractionation, sorry, this is being funky. Fractionation is a process that changes isotopic ratios away from their global average. And it turns out that photosynthetic organisms like plants can induce fractionation. So plants prefer carbon-12, the lighter isotope of carbon. And so when plants are quite abundant, they take up a lot of carbon-12 and incorporate them into their biomass. So let's write this as a flow diagram. So when plants are abundant, there is a high C12 to C13 ratio in plants, which means that the rest of the carbon pool globally, so in the atmosphere, is lower. So there's a low 12C to 13C ratio in the atmosphere. Well, atmospheric carbon dioxide dissolves in the ocean to make bicarbonate. And so what this means is that because there's a low C12 to C13 ratio in the atmosphere, there's also a low C12 to C13 ratio in ocean bicarbonate. So this is the bicarbonate ion that I'm writing here. And so what that means is that the calcium carbonates that form in ocean sediment are heavier. In other words, they have more C13 relative to C12. Okay? So heavier CaCO3 in oceans. When these carbonates are deposited in ocean sediment, they're eventually lithified and incorporated into the rock record. So I'll say heavier CaCO3 in oceans and the rock record. So when we look at the rock record, what isotopically heavy carbon indicates is a fast rate of organic carbon burial due to a lot of plants photosynthesizing. And when plants photosynthesize, they produce oxygen at a rapid rate. So the bottom line, let me put this in another color here. Let's choose blue. So the bottom line here is that heavy, meaning having a lot of C13 relative to the global average, so heavy carbon in the rock record leads us to infer high oxygen in the atmosphere because there are a lot of plants that are photosynthesizing. So I'll just say right up front, when you're studying for the exam, this is a really important key point to understand and also to remember. So the way I like to remember this is that plants are taking up carbon dioxide through these really tiny pores in their leaves. And so kind of the mnemonic device that I use to remember this is that it's easier for light carbon to get into these really small pores. And so when there are a lot of plants, they're taking up a lot of light carbon. The rest of the atmosphere becomes heavy. The oceans become heavy, and the sediment that's deposited within those oceans and incorporated into the rock record also becomes heavy. So heavy carbon in the rock record means high oxygen in the atmosphere just because there are a lot of photosynthesizing plants. Okay, that's a helpful way to think about it. So you'll usually see diagrams where you have geologic time on the x-axis and carbon isotope on the y-axis. And you can interpret these heavier carbonates, higher on the y-axis, as meaning more oxygen in the atmosphere. So one of the things that you've learned in your in-class activity is that during the Carboniferous period, extensive coal deposits formed due to the high rates of production of organic matter within swamps. And so during this period of time, plants were very productive, oxygen was high, and carbonates were high within the rock record. So this is going back in time. And this is going forward in time over on this side. Okay. I think I'm going to pause here and get into oxygen in the next video.